For this demo, I have an Android emulator running Jelly Bean. The application we will use for test is a simple activity with a button. When you press the button, it pops up a toast message telling you it has popped the toast. It is nothing fancy, and the code is not incredibly interesting either. As you can see, it has a simple onCreate and onClick method which do all the work, but the simplicity is okay, as our focus here is to look at the sandbox the app is placed into by the system. The application package is com.pluralsight.example.toastpopper, which, as we will see in a moment, we can use to find the running process on the system. Let's open the DDMS perspective and take a look at what is running on the device. Looking at the running package list in DDMS, we find our test application by package name. Here we can see our package by name along with some additional information. The column adjacent to the name is the Linux process ID of the process running our app. The columns to the far right are network port numbers used by the debugger to attach to the process. If we click on the process, we can see some additional details about the process, such as thread information and heap usage, if the features were enabled in the app or turned on in DDMS. If we enable thread viewing in the app, we can see a snapshot of the threads running in the process. We will look closer at the threads within the Android Threads module later in this course. For now, we are interested only in the process in which our application is running. One thing you will note is clearly absent from the package details is the user identity which is executing this app. For that, we will need to move to a shell on the device via ADB. Similar to a regular Linux system, the ADB shell provides us with the CLI in which to interact with the system. In ADB, we have some familiar commands such as ps available to us. Using ps, we can see the running process list for the system. One of the first things you may note is there are a number of processes shown in the list which are not in the DDMS application list. This is because DDMS uses a special debug interface to talk to the Android framework, so it knows which processes are actual Android packages. Looking closely at the process list, we can see more detail about the processes, including the user ID. Unfortunately, this limited version of PS only shows us the username and not the numeric ID. The default on Android is for packages to get assigned IDs starting at 10,000. So in our example, we can see the ToastPopper app is assigned U0_A46, which corresponds to user 0 app46. Note that with only a couple of exceptions, the Android package processes each have their own user ID. We will see how to leverage this functionality later in the course. As you can see, each package is running within its own process, and each process has its own execution identity. Let's take a look at the other key aspect of the Android sandbox, the file system. Unless explicitly installed to external storage or dealing with multiple real users, packages are installed to /data/data. External storage installs utilize an encrypted file system store layered on top of the storage medium, usually SD cards formatted with a FAT32 file system. Similarly, multiple end users calls multiple data areas for apps on the file system. But the information we are about to cover with respect to package file system sandboxes still applies, since the encrypted file store uses a Linux-style virtual file system, and multiple end user data space is also unique per real user. Within /data/data, you will find a directory which corresponds with our application. Note the owner of the directory matches the user ID of the process in which our application is running. Also note the permissions on the directory. For those unaccustomed to Unix-style permissions, let me explain the fields. The D on the far left column stands for directory. If this were a hyphen, it would mean the entry was a regular file. There are other possible values as well, but for our purposes they are unimportant. The next three values are the permissions for the file owner. You will notice that each directory file entry has the R, W, and X indicated for the file owner. These are read, write, and execute permissions respectively. This gives the owner full permissions to perform any file system operations he or she may want. The next set of three characters are the group permissions. Here's where things get a little more interesting. Note that only the R and the X are set. So a process running with a user identity that is part of a group could read or transverse the directory, but not write to it. Finally, we have the world permissions, or anybody else, which are all hyphens. This means there are no permissions set for all other users. Therefore, only processes running with the user identity or belonging to the correct group can even read or go into the packages directory. And Only a process executing with the owning user identity can write to the package. Since we are running on the emulator, our shell is running with full superuser permissions. Let's switch to a commercial device, an unrooted Nexus 7, and attempt to list the /data/data directory. You can see here we have a very different result. Notice that ls is unable to list the directory because we do not have permissions to do so. The reason is, of course, execution identity and permissions. If we dump a PS list and look for the shell, we can see that its user ID is shell. Switching back to the emulator ADB instance and doing the same, we can see the shell on the emulator runs as root. This is why on the emulator we can freely browse the /data/data directory. As we have seen, apps under Android are confined to their own sandbox, and the system enforces permissions to keep them rather isolated. But apps definitely communicate with each other in modern systems, and Android is no exception. So how do you do this in Android? Traditionally, in Unix-like systems such as Linux, IPC was performed using System 5 or BSD IPC. These are tried and true methods, but they are not well suited for small embedded mobile devices such as Android. The APIs are large and complicated and have a fair amount of overhead associated with them. While Android is feature-rich and growing all the time, we have to keep in mind it is running on an embedded, resource-constrained device. Ideally, any IPC mechanism we use needs to be as resource-efficient as possible. Another option is a local network socket or a Unix domain socket. These are available on Android and in some cases already in use. For example, the phone application and the underlying RIL within the telephony framework use Unix domain sockets for communication. While it is a generic medium and quite flexible, it is a little too open-ended and not necessarily the most efficient. To solve this problem, Android provides a number of facilities in which apps can perform IPC in an efficient manner. The first of these is called the intent. Intents are special IPC messages which contain data in a standardized format. Messenger objects are special cross-process objects which allow one process to send a message object to a handler object running within a thread executing as part of another process. Content resolvers are another facility for doing IPC, though it is targeted specifically at data storage. iBinder and binder objects provide a highly efficient IPC mechanism which allows for processes to share memory and therefore objects. Intents are very pervasive in the Android platform. An intent is a basic communication medium which is very message-like and extensible. Each intent contains certain characteristics which are considered addressable within the platform. The action and category fields within the intent provide the framework with information it needs to properly route the intent. This flexibility allows customized intents which are tailored to your application, as well as the ability for packages to override default behaviors. For example, the launcher or home screen is the main interface seen by users when the phone first boots and is central to user navigation. The launcher is just another app package which is responding to a certain intent, one which includes the category android.intent.category.home. There are alternative launcher applications available, which once installed are registered with the system to receive this type of intent. Intents can include additional payload which is specific to the application. Data can be specified as a URI object or other types of string-related objects, or it can be custom data placed in something called extras. Extras can be simple primitives as well as custom objects which can be included in a bundle object. For example, when using an intent with the action android.intent.action.dial, your app must include a data URI object which has the dial string included in it. The framework efficiently routes the intent and its payload to the appropriate process. This allows one app to effectively call another app running in another process to do some work. In most cases, you fire an intent for another app to do something the user requested. This has the added benefit that apps can take advantage of other apps in a plug-in type fashion. As an example, your app does not need to know how to send an email. It can just send an intent requesting an email send with the appropriate information, and the system will start the correct app to handle it. However, it is also possible to fire an intent and wait for the other application to complete it. This essentially results in a simplified remote procedure call with restricted inputs and outputs. Another IPC mechanism available in Android is the messenger object. This object allows one process to send message objects to another process. Under the hood, the messenger is a reference to a handler object running in one process which can be shared with another process. This means the receiving process must support the messenger as well as publish or document the message objects which it supports so other apps know how to communicate with it. We have not talked about message and handler objects yet, as they are typically used within threads of an application. We will discuss these in more detail in the module on worker thread options. The handler message paradigm is used heavily within Android, so the advantage of having messenger object support in your application is the API set and operating conditions are very familiar. Content resolvers are another IPC mechanism available in Android. However, unlike the intent, which is a generic message-like architecture, the content resolver is focused on data management and storage. Content resolvers are used to interface with content providers. These providers may reside in your own app, and therefore the same process, or they may reside in a separate app and process. This flexible architecture allows one process to effectively track and store data, while any number of other processes may operate on the data as well. A great example of this is the Android contacts database. Content resolvers, being very data-centric, support a number of operations which should look familiar to app developers used to working with SQL databases. Primitives such as insert, delete, and query are all available and operate on the same cursor objects used to work with databases. Content resolvers also support calling methods defined on the specific content provider. This allows for efficient RPC functionality, though it is constrained in its inputs and outputs just like the intent. The reason for this will become clear as we move to the iBinder. Finally, we have the iBinder and binder. This is the base IPC mechanism in Android. The binder framework is what all of the previous IPC mechanisms utilize under the hood. As such, the binder framework is an extensible construct available for use in your apps, though it is also not for the faint of heart. The binder framework utilizes a special feature added to the Linux kernel as part of the Android open source project. This feature provides efficient sharing of memory across processes, as well as perform transactions across the processes. Data objects are transferred through the binder using a special serialized format. The memory containing the data is then shared across the process boundary via the kernel support. The data serialization is different than the Java-defined serializable interface. Instead, Android defines a parcel object, which marshals the data. Parcels can handle certain objects such as strings and array lists, as well as custom objects. However, the use of custom objects requires them to implement the parcelable interface. The parcelable interface allows your objects to be reconstructed on the other side of the binder, so the other process can utilize it. iBinder and binder objects can also be used to call methods in another process. Services defined by the Android framework, such as the notification manager, utilize this mechanism to execute service methods running in the main system server process on the platform. The iBinder utilizes the transaction mechanism defined by the kernel edition to call a method implemented in another process and wait for it to return. Note, however, that exceptions are not thrown across the process boundaries. Defining your own custom interface using an iBinder is done using AIDL, the Android Interface Definition Language. Let's take a look at an example of IPC, and for this example we're going to use intents. In this demo, we will create an intent to launch a web page and send it. In order to clearly show the IPC in play, we will actually do this via two apps, with one acting as a simple relay or proxy.